ways that are not sedimentary, and they can really muck you up. The first are volcanic breccias, and those often are truly sediments. So you're sitting on a volcano, you have a huge explosion, it blows the top of the volcano to smithereens. All those big chunks of rock form a mud flow down the side of the volcano, and I have a matrix-supported volcanic-classed breccia. And that is really a volcanic-classed conglomerate. That is something that we call a sedimentary rock. But you can do the same thing below the Earth's surface. You've got some rock sitting there, it's all happy, a bunch of steam comes up. You have a steam explosion in the subsurface, and it shatters the rock. And then hot fluids come in and alter some of it to mud and get silicified. And so you have a rock that looks like a breccia, but it never was on the Earth's surface. And so these you've got to watch for. They can fool you if you're working in volcanic terrains. And you have to hope sometimes you can see that, oh yeah, my breccia is forming a dike between other rocks. But other times it's really hard. I've been working in things like volcanic necks. It's like, well, is that a sedimentary breccia or is it a volcanic breccia?
Good example location?
What?
Is there a good example location?
There are many. Actually, it's real common in volcanic terrains. The place I've seen them, Cripple Creek, bunch of them in central Arizona, the Potrios, if you're looking at some of the insides of the cones in the Potrios, you can see that kind of problem. Where else? Oh, the southern end of the Quitman Mountains, there's one that was real problematic. Right where the road comes up from Indian Hot Springs up around the southern end of the Quitmans. Those are the ones that come right. Oh, and then in the Precambrian, I've had all sorts of issues there. I was working in, and actually that was something I don't have here because it's so weird, but I was working on these rocks, Precambrian rocks up in north of Michigan in up north of Lake Huron. And you're walking along through these nice mud rocks, and all of a sudden you have this monstrous breccia with stuff from 2 kilometers down and 1 kilometer above all mixed together. And then they define these big pipes. What the hell? And there's not much in the way even of volcanic rock. Sometimes you have a few little things that are hot fluid, but mostly it's just sitting there. It's like all these rocks mixed up, and they finally figured out they're meteorite impact breccias. That somewhere up on the surface, you hit the Earth so much that it sort of knocked down a chunk of rock and it rebounded and mixed everything up. So those are weird ones. The other really common one is solution breccias. And you have limestones or evaporites, things that dissolve easily. And you get water flowing through them, again, not at the Earth's surface, and it'll dissolve them away. And you'll end up with this wild breccia that's not made at the Earth's surface. It's made in caves below the Earth's surface.
Like Florida?
Like Florida today. The Franklins are full of this stuff. People come from all over the world to look at the Ordovician and Silurian solution breccias in the Franklins because in central Texas, they're oil reservoirs. Another good location for this stuff is in Colorado. There's a real famous formation called the Molas Formation that is sitting on top of Mississippian rocks there, and drove people crazy because it was huge chunks of limestone floating in this bright red mud. Drove people nuts, and they finally figured out the whole formation is a solution breccia. But it was actually called a formation. Any questions? Okay, finally, for the formations, and we've already touched on this, is it a pure conglomerate or does it have sand in it? Your book uses these terms, and we're just going to call them sandy conglomerates, like we said before. I'm just repeating what I said on that. Okay, questions on conglomerates? What time is it? I keep looking at that clock thinking, oh, we've got gobs of time. It's still 8:45.
Clock hasn't moved since this semester.
I know. Okay, sandstones, is it a pure sand or does it have lots of conglomerate or clay? In other words, is it a sandy conglomerate or is it a clay? If it's more than 90% sand kinds grains, it's a sandstone. In particular, we call it an arenite. If, say, you've got 20 to 50 or 10 to 50% sand, and 20 and let's see, I gotta get my numbers right. 10 to 50%. Excuse me, 10 to 50% mud, and 90 to 50% sand. So more than 50% sand, but not 90% sand. It's called a wacky. And that's a German word for, it actually stands for soup, for stew, for chunks of things floating. And so a wacky, in this case, means a muddy sandstone. And we're going to find them again in carbonates. But so, and then, so if it's pure, if it's more than 90% sand, it's an arenite. Less than 90% sand, it's a wacky. Less than 50% sand, it's a mudstone. And then we go by composition. And here, this is in your book, same exact triangle. And we then do it on composition. And if it's more than 90% quartz, it's a quartz aronite. If it's if it's less than 90% quartz, but it's and the stuff that's in it is mostly feldspar, it's a feldspathic aronite. And then if it's more than 50% mudstone, it's a lithic, rock fragments, it's a lithic aronite. Does that make sense? So if I've got a rock composed of 15% feldspar, 70% rock fragments, and 15% quartz, plot like right there, it's a lithic aronite. You guys know how to use these triangular diagrams? Anybody have any trouble with this in interpreting it? Same thing for wackies, except now we add in mud. If it's got some mud in it, it's the same composition, but now we just call it a wacky instead of an aronite. So if it's 20% mud and 80% quartz, it's a quartz wacky. If it's 70% quartz, 20% feldspar, and 10% mud, it's a feldspathic wacky. Anyway, and here's just what some look like. Here's a quartz aronite. It's all quartz. These are all quartz grains, and this actually, all the porosity's been filled with quartz cement. So this is a quartz rock. Here's a lithic wacky. I'm going to turn down my things. Y'all can see this is a fossil fragment. Got a carbonate grain here. Got a couple of volcanic grains. And we have two special names for different kinds of sandstones that you'll see a lot in the literature that are real, you should know. The first is if you have a lot of potassium feldspar, so you have a pink or orange rock full of lots of pink volcanic potassium or igneous potassium feldspar fragments, we call it an arkose. And it's important because that means you're eroding a granite to make it. And so arkoses tend to mark mountain building events where granites get pushed up to the Earth's surface. Gray wackies are rocks that are made of lots of mud and lots of volcanic rock fragments and lots of plagioclase feldspar. And they are just the ugliest gray Arkoses are kind of pretty. They're these beautiful pink and orange rocks. Gray Rockies, you're sitting there going, is it a mudstone or a sandstone? That's the ugliest rock I've ever seen in my life. But they form next to volcanic arcs. And so again, they're very important for marking tectonic events. Questions? Okay, we're on time.
I do have a question. You said the Arcos, where is that formed again?
Arkoses form where you uplift granites, so they tend to mark mountain building events. Where granites are pushed up to the Earth's surface by big faults and things. Anything to add?